Okay, now we'll continue with the inverting non-one-to-one functions. Okay, and f of x equals to x square, and f of minus a equals to f of a. That means that's the even function, okay, as we know that. And you know that these functions normally graph must be whole black curve, okay, but that's the y function, okay, and the y equals to x square. But if you select the domain of the f of x functions, okay, by the from 0 to infinity, that means that this is the sub-interval, okay, and let me write that function is capital of f. It's same f of x equals to x squared, but it's defined on the domain which is 0 is less than or equal to x is less than or equal to infinity, okay, and in this interval, okay, our function, okay, can be inverted, okay, and so that, as you see, okay, any horizontal line, okay, like that, okay, horizontal line, okay, at the right hand side of the y-axis, okay, as you see, intersect only on the 1 points, okay, so this curve can be inverted, and the inverse function will be like that, which is the y, okay, equals to capital of f minus 1 of x equals to square root of x, okay, and let's talk about the derivatives of inverse functions, okay. If y equals to f to the minus 1 of x inverse fx, if and only if x equals to f of y, okay, and the a is less than y and it's less than b, okay, and let y equals to inverse fx, and we want to find derivative of y, that means del y over del x, and we must solve the equation y equals to inverse of x for x equals to f of y, and differentiate implicitly and we respect that x to obtain one equals to f prime of y times del y over del x, so del y over del x equals to 1 over f prime of y, and we can write the derivatives of the y, del y over del x, 1 over, okay, and the f prime, and we know that y was inverse of x, okay, f prime of inverse of x, okay, and it can be written del over del x times, okay, and the f inverse of f x. That's the inverse of derivatives of the inverse functions, I'm sorry. And let me write an example to understand this derivation clearly, and show that f of x equals to x cubed plus x, and nothing that oops, is 1-to-1, okay, on the whole real line, which is the domain of this function, and noting that, okay, f of 2 equals to 10, okay, and find the, okay, inverse of f prime of 10, okay, and let's solve this question. Firstly, let me take the derivative of the f of x function, okay, I mean that f prime of x, this is polynomial function, so it will be 3x squared plus 1, right? And we know that it's greater than 0 for all real numbers because of the x square, okay? And for all real numbers x, f is increasing and therefore one-to-one function and invertible. My friends, this is important. This is increasing and it's larger than 0 for all real numbers, okay, so that we can say that function is f prime function is 1-to-1. so it's invertible, okay, and if y equals to inverse f, then okay, x equals to f of y, and which is equal to y cubed plus y, okay, so that 1 equals to, okay, and the f prime of y, and that means the 3y square y, okay, times y prime, okay, and the y prime equals to 1 over 3y square plus y, okay, and if f of q equals to 10, so we can say the inverse f of 10 equals to 2, which is equal to y, okay, so f inverse of f 10 prime equals to, okay, 1 over 3y square plus, I'm sorry, that must be, I think, the 1, right? And let me correct this part of the question. This is 1 and this is 1, so correct this part again, and the 1. So evaluation bar y equals to 2, so it equals to 1 over 3 times 4 plus 1, so it equals to 1 over 13. Okay. And let me continue with the logarithms, okay. And the function f of x equals to a to the power of x is a, okay, 1-to-1 function, okay, and provided that a is a positive number, that means the a is larger than 0 and the a does not equal to 1, okay, and so if a is larger than 0 and a does not equal to 1, okay, the function inverse of f, that means, okay, the function which is the logarithm, okay, of x to the base a, logarithm, okay, of x to the base a, okay, which is the inverse of a to the x function, okay. So y equals to logarithm of x to the base a, okay, if and only if x equals to a to the y, and the a is larger than 0 and a is not equal to 1. Okay, so that's the logarithm function, and we must know that the cancellation identities, okay, about this logarithm function, okay, and the first one, don't forget it, and the logarithm, okay, of a to the x to the base a equals to x. This is the cancellation identity 1, and the second identity, it will be a to the logarithm of x to the base a, so it's equal to x, and that's the for all real x, and that's the for all x is larger than 0. Okay, this is the cancellation identities. And let's continue with the laws of logarithms. If x is larger than 0, y is larger than 0, a is larger than 0, b is larger than 0, and the a is not equal to 1 and b is not equal to 1, okay, and the first, second, third laws, let me write it. Logarithm, okay, of the 1 to the base a equals to 0, okay, and the logarithm of x times y to the base a, it equals to logarithm of x to the base a plus logarithm of y to the base a, okay. And the third one, logarithm of 1 over x to the base a, it equals to minus logarithm x of x to the base a. And the fourth one, fifth one, and the sixth one, continue, and the logarithm of, okay, x over y to the base a, okay, and it equals to logarithm of x to the base a minus logarithm of y to the base a, okay, and the fifth one, logarithm of x to the y, okay, to the base a, it equals to, okay, y times logarithm of x to the base a, and the sixth one, that's important, okay, logarithm of x to the base a, it equals to logarithm of x to the base b over logarithm a of a to the base b, okay, and that's the last law for logarithms, okay, and let me continue with some examples about these functions. Examples 1. And the first one, logarithm of 10 to the base 2 plus logarithm of 12 to the base 2 minus logarithm of 15 to the base 2. As you see, all of the logarithms on the base 2, okay, to the base 2, so we can merge all of them by the multiplication and the division, okay, so it will be logarithm, okay, of 10 times 12 over 15, okay, to the base 2, okay, and some cancellation, and after that you will obtain logarithm of 8 to the base 2, okay, and we know that that is the logarithm of 2 to the 3 to the base, okay, 2, so we know that that's equal to 3 times logarithm of 2 to the base 2, so it equals to 3, right? And another example, logarithm, okay, of a cube to the base a square, okay, and that's very simple, but let's write it, 3 times logarithm of a to the base a square, okay, and you can write this part by 3 over 2 times logarithm, okay, a square of a square to the base a square, okay, and if it comes here, okay, you must divide it to this part, okay, as you see, and we know that this part will be 1, okay, and it's equal to 3 over 2. Third example, and this is the simple cancellation example, okay, 3 to the logarithm of 4 to the base 9, okay, and it equals to 3 to the power of logarithm of 4 to the base 3, okay, over, okay, I use now 6th law, okay, please look at the 6th law, and over logarithm, okay, of, I'm sorry, logarithm of 9 to the base 3, okay, and the and after that it can be written by the, okay, oops, let me write this example again, okay, and because of this step a little problematic example, okay. Firstly, I must tell another identity, and after that I must solve this, okay. So let me choose the another example, which is the 2 times, okay, logarithm, okay, 12, logarithm of 12 to the base 3 minus 4 times logarithm of 6 to the base 3, okay. So it's equal to 2 times, okay, and the logarithm of 3 to the base 3, okay, plus logarithm 4 of 4 to the base 3, okay, and the minus 4 times logarithm of 3 to the base 3 plus logarithm of 2 to the base 3, okay, and that's the 2 plus 2 times logarithm of 4 to the base 3 and the minus 4 and the minus 4 logarithm of 2 to the plus 2 to the logarithm of 2 to the base 3 again, okay, and this part will be, and this will comes here, so minus 2, okay, plus 4 logarithm to the 2 or to the base of 3 minus 4 logarithm to the 2 to the base of 3, okay, and this parts will be cancelled, okay, and after that that will be minus 2. And now let's continue with the natural logarithm. And exponential. Okay, and the ln x, okay, that's the natural logarithm of x, okay, and the ln x, it equals to logarithm of x to the base e. We know that e number is Euler number, okay, and the e equals to 2.718. This is the irrational number, and don't forget it. Okay, and we know that inverse of natural logarithm equals to e to the power of x, so it's the exponential function. Okay, and the exponential function is the special part of the a to the power of x power function. Okay, and let's continue with the derivatives of integer powers, and remember how to evaluate the ln x derivation. Okay, and we know that the f of x and the f prime of x. What are these? That's the x cubed. We know that this the 3x square. Okay, and after that x square, it's equal to 2x. Okay, and the x to the power of 1, and it's equal to 1. Okay, we know that x to the power of 0 equals to 0. Okay, and the x to the minus 1, power of minus 1, it's equal to minus x to the power of minus 2. Okay, and x to the power of minus 2 is equal to minus 2 times x to the power of minus 3, and these polynomials goes on like that. Okay, and what about the, as you see, x to the minus 1, okay, it equals to 1 over x. Okay, and if f of x equals to, okay, ln x natural logarithm, that means, okay, and don't forget it, f prime of x equals to 1 over x. Okay, don't forget this part. And let me write the definition. For x is larger than 0, let, okay, a sub x is the area of the plane region bounded by the curve y equals to 1 over t. Okay, and the ln x equals a sub x if x is larger than or equal to 1, and the minus a sub x, okay, if 0 is larger than, x is larger than 0 and the x is less than 1. Okay, and the ln 1 it equals to, okay, we must know that 0.